Hello, my name is Derek Sattler. I'm a researcher with the Canadian Forest Service located at the Pacific Forestry Centre in Victoria. I'd like to thank the organizers for inviting me to present at this symposium. As well, I'd like to thank the other researchers with whom I've worked with in developing these Rust modules. For the current presentation, I'll go over some of the recent additions to these Rust modules. So before going into the recent additions, I'll provide a brief history of the Rust modules. Over the past 5 years or so, myself as well as other researchers with the province have worked on developing two Rust modules for use in the TAS2 Growth and Yield Simulator. For those who don't know, the TAS simulator is used to project the development of managed stands over time. It is most often used in silvicultural planning and in the timber supply review process. The two models are called GRIM for Western Gall Rust and Crime for Commander Blister Rust. These rusts infect hard pines, and within the province of BC, they are generally found on lodgepole pine. In areas of the province where these two rusts are prevalent, there is concern that they could have impact on harvest volumes. Unfortunately, there is no field data available that would allow us to directly link levels of rust incidence at an early age to losses incurred at rotation. Thus, as an alternative, we gathered the data that was available and attempted to simulate the effects of these rusts in the TAS growth simulator. The modules have been programmed into TAS and have currently been programmed into TAS and have application in both silvicultural planning and timber supply review. So before going into the recent additions, I'll provide a brief history of the Rust modules. Over the past 5 years or so, myself as well as other researchers with the province have worked on developing two Rust modules for use in the TAS2 Growth and Yield Simulator. For those who don't know, the TAS simulator is used to project the development of managed stands over time. It is most often used in silvicultural planning and in the timber supply review process. The two modules for rusts are called GRIM for Western Gall Rust and Crime for Commander Blister Rust. These rusts affect hard pines, and within the province of BC, they are generally found on lodgepole pine. In areas of the province where these two rusts are prevalent, there is concern that they could impact volumes at rotation. Unfortunately, there is no field data available that would allow us to directly link levels of rust incidence at an early stage of stand development to losses incurred at rotation. Thus, the alternative was to gather the data that was available and develop individual equations to simulate infection, rust-induced mortality, and the formation of galls on live trees. Together, these individual equations attempt to simulate the effects that these rusts have on planted pine stands. The modules have been programmed into TAS and have application in both silviculture planning and in the timber supply review process. For more on how these modules are used in TSR, I recommend you see the presentation by Dave Waddell. The field data that was available to assist in the development of the modules was collected from various experimental projects known as EPs. EP671, for example, was used extensively, and you see some of the other ones that are presented here. This data was key to the development of the modules. This is because each data source represented long-term time series data in which the initial planting density was known. Although these research plots were not designed for the purpose of serving rust initially, those in charge of the EPs had the foresight to begin recording occurrences of rusts from a very early age. Furthermore, several of the trials were designed to test the effects of planting density on growth. So this allowed us to see if rust impacts differed depending on initial planting density. One of the common characteristics to all the test sites where rusts were found is that new infections were rarely seen beyond stand age of 15 years. So if you look at the figure on the right, where you have on the x-axis years since establishment, and on the y-axis the cumulative incidence of first infection in percent, you see that they generally plateau at around an age of 15 years. So this is an important point that will be brought up in later slides. Focusing for the moment on Western gall rust, what is shown here on the figure on the left are some of the initial tests of the rust module. The figure shows a comparison of observed and task-predicted volumes for infected and uninfected components of plots that were used in model development. For example, the top two panels show observed and predicted volumes for one stand that was planted at 500 stems per hectare and had a roughly 50% gall rust incidence rate at age 15. The top left panel shows the stand volume of infected trees, while the top right panel shows the volume for the same stand but for the uninfected trees within the plot. The panel below shows the same thing, but for different initial planting densities and different incidence levels. The same is shown in the last pair of panels at the bottom. In most cases, we found that when the rust modules were used in tasks to project stands, there was good agreement with the observed data. A final step was to use SawSim, which is a lumber manufacturing simulator that is linked to tasks. In the case of Western gall rust, the infected trees that survive until rotation will contain galls that will require removal. Consultation with industry indicated that galls that encircled more than 50% of the main stem had to be removed. So an equation was added to SawSim, which predicts the location of these large galls along the stem. SawSim is then instructed to remove a 12 centimeter section around the gall before transforming the log into lumber. And this is somewhat depicted in the figure on the right. Again, focusing on Western gall rust, the current figure shows the expected relative loss in merchantable volume and lumber volume at a harvest age of 70 years. On the x-axis, we have the rust incidence level at age 15. The figure on the left shows the relative loss in merchantable volume for 4 initial planting densities, shown in the legend. The losses are relative to an equivalent stand that has not been infected. What becomes clear from this figure on the left is that one can minimize their relative losses by planting at a higher initial planting density. And one could use this as a tool to plan planting densities in areas where Western gall rust is of concern. The figure on the right shows the relative loss in terms of lumber manufacturing. Again, the losses are relative to a stand with no rust. Because it shows lumber volumes, it is factoring in the additional loss of volume after the removal of large galls on the main stem. Finally, we see here a figure showing the results for commander blister rust. The impacts from this rust on lodgepole pine are much more severe than Western gall rust. On the x-axis, we have total age, and on the y-axis, we have merchantable volume in terms of cubic meters per hectare. The figure here shows a stand that was planted at 1,000 stems per hectare. If we compare the stand with no commandra to one where rust incidence at age 15 was 90%, we see a reduction at age 100 of nearly 300 cubic meters per hectare. The shaded lines in between represent 30%, 50%, and 70% incidence at age 15. So moving on to some of the more recent additions to the rust modules. To initialize the rust modules in tasks, one must provide an expected value for rust incidence at age 15. The initialization of the modules at this age was selected for 2 reasons. First, we saw in an earlier figure that the number of new infections generally plateaus around age 15. And secondly, Most free-going surveys are conducted around this time, with surveyors also recording the percent incidence of various pathogens and diseases, including rusts. This was convenient for application of the modules in TSR. For each opening, the timber supply analyst would consult the column in the results table where the incidence level for Western gall rust and Camandra is recorded. Yield curves could then be adjusted to account for the expected losses in volume due to rusts. Again, this topic is addressed in more detail in the presentation given by Dave Waddell. Recognizing that not all free-going surveys and results are performed at age 15, a method was devised to adjust the incidence level taken at an earlier age and to standardize it to an age of 15 years. This method is depicted in the equation shown in the next slide. Turning again to the data collected at the experimental plots, a regression model was formulated which allows the timber supply analyst to obtain an estimate of incidence at age 15 from a survey performed at an earlier age. The parameters in the equation, shown here as beta 1 and beta 2, were estimated from the data, which you see in the main figure of the slide. On the x-axis, we have the early incidence of Western gall rust. The age at which the incidence level was recorded is listed in the top panel of each figure. On the y-axis, we have the incidence age at age 15. The solid line is the prediction obtained from the regression model. It is clear that when the survey is performed at a very early age, say for example, age 6, which you see in the top left panel, the relationship between early rust incidence and incidence at age 15 is not as strong as, say, when the survey was conducted at age 14, which you see in the bottom right panel. However, the model performed well and gave an overall R-square of 73%. The small insert figure on the bottom left simply shows how the root mean square error improves as the stand age at assessment approaches 15 years. So with this adjustment method in place, we can now turn our attention to openings in the results database that had not been surveyed for rusts. So the goal for these openings was to estimate rust incidence level at age 15. One option would be to simply calculate the average rust incidence by Beck subzone using openings where rust were recorded. This average value would then be applied to any opening that had not been surveyed for rusts. However, this approach would not take advantage of some of the climatic and biophysical data that was available for each opening. Previous studies had shown that rust incidence levels could be correlated with various climatic and biophysical factors. So the next option was to develop what is called a hurdle model, and that we see here with the equation presented under option 2 in the slide. And a hurdle model consists of two equations. One that predicts the occurrence of rusts, which is the first equation circled in yellow, and one that predicts the expected incidence of rust at age 15, given that it is present, which is the second part of the equation and also circled in yellow. After proposing this option, we went ahead and built a hurdle model using the results data gathered from the Mackenzie TSA. A summary of the data from the Mackenzie TSA is shown in the set of figures presented here. Again, this data comes from openings in the Mackenzie TSA that had been surveyed for rusts. On the left, we have the number of openings in the results database where Western gall rust was noted, and I've separated these by Beck subzone. We can see that the majority of the stands had between 5 and 15% rust incidence levels at age 15. On the right, we see a similar figure, but rather than showing the number of openings, we have the total amount of area by incidence level. I've added this figure simply to show the extent of the openings in the Mackenzie TSA that had been surveyed for rusts. So the data set that was used to develop the hurdle models covered a wide range in terms of longitude and latitude and was present in each of the four main subzones within the Mackenzie TSA. So it turned out, after examining data from the Mackenzie TSA, that any opening that had a pine component that exceeded 10% had at least some level of rust. Since this was a rather simple filter to apply, there was no need to develop a presence-absence model. This would have been, as you recall, the first part of the hurdle model. Nevertheless, I wanted to present this as an option here, as it may be useful when developing similar models for other timber supply areas. But since we didn't need to develop one for the Mackenzie TSA, we can move directly to the part of the model that predicts the expected incidence of Western gall rust, given that it occurs. As previously mentioned, we looked at biophysical variables as well as seasonal climate variables as potential predictor variables of rust incidence at age 15. The climate variables for each opening were obtained from Climate BC. They included variables like spring relative humidity, summer mean temperature, and fall climate moisture index. As can be expected from the results database, there was a considerable amount of variability in terms of Western gall rust incidence in relation to the potential predictor variables. Nevertheless, some variables present stronger trends than others. Here I show three of those variables. On the left, we have the relative humidity in spring, followed by the mean coldest monthly temperature, and lastly, on the right, we have site index. In the end, the model that performed best on the Mackenzie TSA included the mean coldest monthly temperature, the relative humidity in spring, summer evapotranspiration, and the proportion of pine in the stand. And in general, these climatic variables tended to agree with previous studies that had looked at rust incidence in various areas of the province. While the variability explained by the model was not high, the R-square for this particular model was 17%, using predictions from the model provided an improvement rather than simply using the average value and applying this value to all openings that had not been surveyed for rusts. The two maps presented here show the observed and predicted rust incidence levels at age 15 for the openings in the Mackenzie TSA. The figure on the left shows the observed incidence levels from openings where rusts were surveyed. Recall that this is the data that we used to build the hurdle models. On the right, we see the predicted values generated from the model. Thus, for the Mackenzie TSA, a timber supply analyst would take the equation shown in the previous slide, along with its parameters, and use it to estimate rust incidence at age 15 for any opening that had not been surveyed for rusts. So to summarize, the rust modules, Grim and Crime, have been developed and attempt to link early incidents to impact at rotation. The modules are run in tasks and are initialized through a user-supplied value of rust incidence at age 15. For openings in the results database that have been surveyed for rusts prior to a stand age of 15 years, a simple equation is applied that adjusts the incidence level to an age of 15 years. For openings that have not been surveyed, a two-equation hurdle model was proposed. A model to predict the probability of occurrence was not necessary since all stands with at least 10% pine had some level of Western gall rust. The final model for the expected incidence of Western gall rust explained roughly 17% of the variability in the data and performed better than using the average value for each Beck subzone. The same approach has been taken for Comanche blister rust and has shown similar results. So what's next for the rust modules? Well, my recommendation is that the hurdle models should be built for each timber supply area where rusts are of concern. But one should note that these are empirical models, and extrapolation from one timber supply area to another is not advised. So hurdle models should be specific to the timber supply area. Next, as more data from research trials where rusts have been monitored comes in, all of these equations presented here can be updated. And I stress that the information from these research trials is the most valuable information because it represents long-term time series data. One remaining question is this: if the rust modules explicitly account for losses due to rusts, should we then modify the operational adjustment factors that are used in tasks? These operational adjustment factors account for losses due to insects and pathogens, of which would be included losses due to rusts. So if we're already accounting for losses through the rust modules, then it would not make sense to account for those losses again in the operational adjustment factors. So this would suggest that we should adjust these operational factors, but to what degree, that remains unknown.